I have my notes up here ready to go. All right. So today we're going to start 3.4, which 3.4 is almost exactly the same as 3.3. So I'm actually going to keep it a little shorter. It's exponential decay. Exponential decay works the same way as increase, and we talked about it a little bit when we first set up the exponential uninhibited growth stuff in 3.3. This is going to work the same way. All right, applications of decay where we're going to lose our percent. So k is negative, right, because we're losing that percent. So the equation is e raised to a negative k. Again, that k represents the percent at which we're losing, so it's negative, times our variable. And so when we take the derivative, right, it's our original function times that negative percent. And so it should come out negative because it's decaying. A couple quick things as I cut and pasted from my other notes when I set this one up. Our quantity should be decaying exponentially with a decay constant. Again, negative means it's a decay constant. All right, so my decay constant should be less than 0. All right, the Q naught is still the initial value. So again, this would be our general quantity where it's decaying. All right, so Q naught is our initial amount that we start with. E raised to the negative k times time. So again, we'd be losing, right? The k means we're losing that percent over our time period. So it's derivative, which again basically is that derivative here in terms of quantity. Its derivative is our original expression, so our initial value, e raised to the negative k times time, and then we multiply by the negative percent, right? The decay constant. Or again, if I rewrite it, it's the amount we have times the percent which we're losing it. All right, so again, basically that's the same thing that we did with the growth case, except for this time our constant is negative because we're losing. All right, to graph this, just understand the behavior of this. Right, it's not growing indefinitely, it's declining. Again, time technically is going off to infinity. We do start at 0, right? Initial amount is where we start, so this would be my quantity. And my initial amount would be my big value, all right? We start with some 100 milligrams of something that's decaying exponentially, and then it's going to come down, and remember, it's going to approach, not cross, approach my axes, but not cross my axes. All right, so again, it's going to, and eventually it's going to be so small we would consider it 0, even though technically it never actually hits 0. And then the steeper this is, the bigger the k value, the quicker it approaches 0. The smaller the k value, the slower it approaches 0. All right, so that's my exponential decay. Its domain is all, not all reals, positives. And its range goes from our initial amount down to 0. And again, never really gets to 0, although technically once the fraction is so small, we do eventually say it's 0. All right, just like with our growth, we have a doubling time. Well, half-life works the same way. And if you've ever taken a science class, they've talked about half-life. Half-life is something that's understood. Radioactive materials tend to have half-lives that we know and understand. And so a lot of times we're going to be looking for it, or we'll be given a function's half-life in our application, just like the doubling time works the same way. All right, so in general, we're going to do an in general case, half-life, and using it to find the growth constant. All right, suppose I'm going to let capital T represent my half-life. All right, so that means after T, whatever T represents, T days, months, hours, minutes, whatever, I should have half whatever I started with, right? 0.5 would be half of what I started with. So I started with 100. Multiply by 0.5, I'll be down to 50. Alright, so solving for t, well, I'm going to use this information and plug it in. So I have 1/2 what I started with, so 1/2 my initial value equals my initial value e raised to the k times time. Alright, divide out my initial value, and again, that will reduce. So on this side, I'm left with the half, the 0.5. On this side, I'm left with the e raised to the k times time. Take the natural log, and so I have the natural log of 1/2 equals k times time, and my time, remember, was my half-life, so it's capital T, and then we solve for it, divide by my k, and so my half-life is the natural log of 0.5, 1/2, divided by my growth constant. All right, and again, Very similar to the doubling time. The difference between the half-life and the double time is the natural log of 2 when we're doubling. Well, it's the natural log of 1/2 when we have the half-life. Vice versa, so that would be if I'm solving for time, if I'm solving for half-life. You could solve for k, right? If I'm given a half-life, it would be the natural log of 1/2. Well, I'd go back to the step here, right? And instead of solving for t, I'd solve for my k. So natural log of 1/2 divided by my half-life. All right, and again, just like with the doubling time, you can remember that or you can remember the process. All right, well, we can do this in general. In general, solving k. So again, given my quantity at some time, so t would just represent any time, could be a half-life, could be something else. Q naught e raised to the k times that time. Solve for k, I divide by my initial amount. Alright, so I've got my quantity at time t, which I'd be given, my initial quantity, which I'd be given, e raised to the k times time, take the natural log of that fraction. Remember, leave that fraction exact, no rounding. And so I would be left with, on this side, I still have the natural log of the quantity at the time that I'm given, the initial amount, inside my natural log equals k times the time, and then we'd solve for k by taking that natural log of our quantity at times t divided by our initial amount divided by the given time, right? Again, very similar to what we did before. We could also find time this way, or if we wanted to find time, oops, not k, t, it would work the same way. Time would equal the natural log of that fraction divided by my constant, right? Again, that's not new. That's exactly the same thing that I did in 3.3. The only difference here is k would be negative, right? K would be negative because I'm declining. All right, so we're going to look at one example of radioactive decay, and then I'm going to pick up more examples in the next video. All right, so an example of radioactive decay, because it's probably the most common type that you see in applications for uninhibited decay. Alright, so a lot of elements decay, like I said, radioactive decay is most common, but a lot of things decay at a rate proportional to their size. Alright, so an example would be iodine 131, has a decay rate of 8.7% per day. Alright, so it's losing 8.7% of its mass per day. Therefore, it satisfies the differential equation, alright, our rate of change in our quantity size, our iodine, per time is negative because it's decay, right? That's what makes it negative. Write our decimal instead of a percent, times n would represent whatever quantity we have. All right, so there's my exponent. Again, same thing that we did in the last set. The difference here is it's a negative out front instead of a positive. All right, find the function that satisfies the equation. Let n naught represent the initial amount of the iodine present at time 0, then graph the function. So it's going to be just kind of a general graph. All right, so n of t represents any quantity of the iodine after time t, and naught would represent how much we start with. E raised to that 0.087, our decay constant, times our time. So there's the equation that would find how much we'd have left. So we'd have to be given the starting amount, and then how long we want to see. So we'd plug in our starting amount and the time, and we could figure out how much iodine of our sample we'd have left after t days. All right. The sketch to graph is just fairly simple. All right, time is in days, so I've got to write my days down here for time. This would be my iodine, 131. All right, we'd start with the biggest amount would be whatever that starting amount, so whatever we have. So if we have 10 milligrams, 100 milligrams, this is where we'd start. 8.7 per day. Again, 8.7 is not a huge percentage. All right, so I probably wouldn't come down super fast. And that's just, again, just make sure you approach that time axis, but don't cross it. All right, you have your initial amount listed. Again, what your axes represent. Time is in days, quantity is iodine, and then again, it should have a slight curve approaching our time axis. All right, so now we're going to use it. All right, suppose that we start with 20 milligrams, so that would be our initial value. That would be the n naught I'd plug into that equation. How much iodine will be present after 35 days? So there would be the time. All right, so I'm going to find n of 35. I'm going to plug in 20 for my, so I start out with 20 milligrams. E raised to the decay constant times my 35 days. All right, now I'm just going to round a few decimal places. 35 days is pretty far down the line, but decays by 8% per day. I probably don't have a whole lot left at this point. All right, so when I plug that in, it comes out 0.952, and then units on it are milligrams. So again, less than a milligram left after 35 days. Not a whole lot. It's decayed almost all away, right? We've lost almost over 19 milligrams of our iodine in 35 days. All right, after how long will half the iodine be left? So we're looking for half-life. So again, there's two ways you can do this. You can either remember that the half-life is equal to the natural log of 0.5, 1/2, over our decay constant. So it would be the natural log of 0.5 divided by that negative 0.87. Again, just like with the doubling time, you can memorize that formula. It comes out 7.96, so I'd probably round that to 8 days. All right, remember units, days. So the half-life is probably 8 days. Every 8 days, it loses half. So you started with 20 in 8 days, about 8 days. You'll be down to 10. 8 days later, you'll be down to 5. Another 8 days, you'll be down to 2.5, and so on. It cuts in half every 8 days. If you forget that, you could always set it up, right? I know I'm looking for my quantity when I'm left with 1/2 what I started with. All right, so if I started with 20 milligrams, I'm going to be down to 10. All right, and you use that to solve. So we get 10 equals 20e to the k times time, and you'd solve for time. All right, so we'd get 10 divided by 20 would give me 1/2, or 0.5, e to that growth constant times our time, natural log, and so I'm left with the natural log of 1/2, 0.87 times time, and then the last step would be divide by the k. All right, which that's exactly the same thing we found here, and so it would give us the same answer. So it's up to you. You can either memorize this, or if you forget it, you can always revert back to this. All right, so we're going to stop there. We'll, again, do one more video where I'll just do more applications of exponential decay, a couple more examples, and then we'll be done with a set of notes. All right, so this will be the last of this set of notes. All right, we'll stop there.